Same as the homeworks. You don't have to there's no file that you need to turn in, there's no experiment, it's all multiple choice questions entirely on Canvas. You get 2 attempts to do it. Think of it as some sort of a review for the midterm because it touches on things that you've seen right from the beginning of the semester. The one thing that you should bear in mind is this particular homework has questions that are multiple choice, but more than one answer may be right. So you might have to read all the answers and kind of think about them. And in some sense, it forces you to cover the entire material and sort of prepare for the midterm. Some of you have already seen and submitted the homework. The rest of you, I encourage you to do it this weekend. We'll just force you to go over the material. Any questions about the homework? Yes?
Since it's on Canvas, is this something that we can start and save our answers and come back to later, or do we need to dedicate time to finish it?
You know, I actually don't know the answer to that because I'm using whatever the Canvas system for quizzes is. Does anyone know if you can start, save, and then come back later?
Yeah.
If it's like the first one, no. If it's like the first one, you just have to take it and be in it, and you can leave it up for a while, but there's no way to save it and then come back to it later.
I accidentally closed mine on the first and it auto-saved and reopened fine.
Did it?
Okay, so there seems to be some browser magic happening here. I'm not entirely sure
So how
what
long
the answer
did
to
you
that
get back in?
It is whatever
How long before you
Canvas
got back in?
defaults to.
5 hours?
Homework 1 grades are available.
I wasn't sure if it was supposed to be.
I hope you've seen them. If there are any questions, you might just post a comment on the box next to it by the homework, and whoever graded your homework will respond to it. If you feel that you've been treated extremely unfairly, just come to me and talk to me. The next announcement is, yes, there's a midterm in class on Tuesday. I've spoken enough about it, but just to remind you, it's a closed book exam. It's in class, so you get whatever the duration of the class is, and hopefully there will be more of you at the midterm than there are today. Yes?
I think you just said Tuesday.
Did I say Tuesday? I mean Thursday,
right?
Thursday, 1 week from now, yes. Alright, the other thing is project proposals are due today. We've put most of you in the groups that you requested. There are still, I just checked this morning, there's still a few left over. Hopefully we'll get that done right after class. So you just need to submit 1 proposal per group. And like I said, also there's a document on, there's a pinned discussion on Canvas about the competitive project. So there's a short description of what the task is. So if you want to switch from a regular project to competitive, you can read that document and make a choice. It's not an easy data set necessarily, but it's definitely something that is of interest to many people. Definitely me. I would like the Android App Store not to have malware. So check it out. If you feel like you are short of ideas for a regular project, you can just switch to the competitive project. Once all the decisions are made and once you've submitted all your proposals, which means basically you have till tonight or with the late penalty till tomorrow night. Once all that is done, we'll send those of you who registered for a competitive project a link to the Kaggle competition page, and you can start submitting. There's some restrictions on how much you can submit and stuff, but yes, question?
It says we're supposed to run 6 algorithms on the data set. Is variations like the 3 different versions of perceptron, does that still count as one algorithm, or?
Oh man, that's like a subtle technicality that I really don't care about. But let's just say no, because we will cover at least 6 different algorithms, entirely different algorithms.
So families of algorithms,
yeah.
Okay.
If the variant is so big that you could just call it a different algorithm, or if I can call it a different algorithm, then yes. In some sense, let's talk about the spirit of the project. The goal is not so much to make you do things, but to force you to explore these algorithms and other annoyances like feature extraction and not feature extraction but feature transformation and all that on a real life data set. Not something that is controlled and well studied where you can just find a classifier and a paper that gives you the answer. That's the point really. So think of this as an opportunity to push the ideas that you've seen in class really. For example, the data set that I posted on Kaggle, in terms of features it's actually pretty small. There are only 360 or something features. But when I did a rough, quick run of basically no cross-validation, literally about a 1-minute experiment on the data set using some off-the-shelf SVM that I've written, it was pretty lousy actually. So it seems like detecting malware is not easy. So you might have to do fancy things like feature transformations and such things as well. So focus more on that rather than the counts. Yeah, so like I said, there's a thread on Canvas that describes this project. You can still read that document, and I really like this thing that's happened this semester, which is every homework there's only one thread on Canvas. I don't know about how you guys feel about that, but I find that extremely convenient to just go over that thread and kind of get an idea of what people are having trouble with, or maybe answer questions rather than multiple things. So we're going to do the same for the competitive project as well. There's a pinned discussion, and that will be the central clearinghouse for discussion for that stuff. Any questions about any of these things? Yes?
So if we're doing a regular project and we submit our proposal and say you have a problem with it or don't think it's good enough or want to see changes, and are you just, do we still get like a good grade on the proposal, or like do you?
So
how does that work? How do you get feedback and make changes?
So let's put it this way: if it's an empty or a completely submission that's devoid of any content, of course you're not going to get a grade. If you don't submit, you won't get a grade. If you made an effort and I read it and I feel like, yeah, this person has thought about this, then yes. And in some sense, like I said in the last class, this proposal is more of a discussion. You send me a proposal, I'll tell you, this is not in scope, or this is impossible, or you need like, this is like 3 PhD theses together. And in which case, I'll initiate this conversation and you'll come back with a different proposal and stuff like that. So the goal of the grade is assigned not just to this one submission, but to the entire process of this thing. And the late penalty is for basically you not initiating that conversation on time, or for you not having done anything. Any other questions?
So,
Yes.
what if we decide upon one technique
Okay.
for the project and we mention that in our proposal,
And you
but
were.
in the end we end up doing something. While it's, the application, the thing will be same, but via some different technique.
Yeah, see, it's not a contract, okay? It's not a legally binding contract. I'm not going to come to you at the end of the semester and say, yeah, in October or September you said this and now you didn't do it, because I understand that sometimes it doesn't work. In fact, if you think it doesn't work, you can tell me in your project final report, this is what I proposed, it didn't work because I tried this and this happened. On the other hand, if you propose, say for example, you're going to do speech recognition, or you're going to detect whether a sound, here's the imaginary project that I'm literally just made up. An audio signal, you have to detect whether there's a human speaking or not. It's a classification task. Let's say you propose that. And then, end of the semester, I see your project report and it's basically a spam detector. It has nothing to do with it. And you just changed and you never told me in the middle comments. There's no, you see how they are two different. On the other hand, let's say you propose that project and you find that you try like 8 different methods and nothing works, and that could be a project. I tried all these things, nothing works, seems like this is a hard problem, it's an open question, and it's totally honorable to say that I did, the fault was not with my experiments, the fault was not with the way I conducted the experiments, but with the data itself. That's totally fine. Sometimes you just throw everything you can at the data, and nothing sticks. That's fine. What I would not be very happy about is the former situation where you propose this human detector and give me a spam classifier. Completely unrelated, and that's not okay. Other questions? If you have any questions about any of these things, send a message on Canvas. We'll try to get back to you soon. If there are no questions, let's move on. At the end of the last lecture, I invited you on this adventure called Computational Learning Theory. We'll start with that now and move on to different ways of measuring learnability. This series of lectures will take maybe starting today, and it will probably end after the fall break. So, as I said, the point of learning theory is to discover, or not to discover, is to answer the question, are there any laws of nature, like Newton's laws, for example, that relate to learnability? And we want to, basically what that means is we want to somehow answer questions like, if I have these many examples, what is the probability that I'll get a good enough hypothesis? And by good enough, that means what's the probability that I'll get a hypothesis that makes a low error? Another way of asking the same question is, if I demand that I cannot live with a classifier whose error is, say, whose error is more than 1%, I cannot live with that, and I need this with this guarantee with high confidence. How many training examples do I need? And this typically, we'll see theorems that relate these quantities, and typically the complexity parameter is the size of the hypothesis class. If your hypothesis class is very rich, you probably need more examples to obtain the same guarantee. So let's get started. I want to start with this example that we've seen before. In fact, we'll be kind of analyzing this as a toy for a while before we get into general purpose theory that does not really care about whether the hypothesis class is conjunctions or not. So this is a slide from before. We're talking about supervised learning where there are some examples, in this case these vectors of zeros and ones, and there is a hidden function f. It's written here, but pretend that it's hidden. There's this hidden function, and the learning algorithm is unaware of this function, and an oracle, nature, labels these examples and gives you a labeled set. So the important thing to note here is these examples are drawn randomly according to some distribution, some natural distribution. For the rest of this conversation, I'll be using the letter D to talk about the distribution of examples. So when I say examples, it's just the feature vectors, not the labels. There is some probability distribution on top of these features. Maybe all ones occurs more frequently than all zeros, and so on. And there is a process out there that samples examples from this distribution, and the oracle labels these randomly sampled examples and gives us labeled examples, or gives the learning algorithm labeled examples. And we saw this algorithm called elimination. What elimination does is it will, first of all, it will discard all examples where the output is not 1. So it will discard this, yes. And then it will eliminate it, and we are assuming that the hypothesis space consists of conjunctions as well. So the hypothesis, every function in the hypothesis space is simply a function that's like the output is 1 if this feature is 1 and that feature is 1 and that other feature is 1. Otherwise it's 0. We have to discover what this, that and that other are. We have to basically fill in these slots. So the way elimination proceeds is it first discards all examples that have a label 0. And remember, here, just for illustration, I am talking about a particular learning algorithm. Very soon we will talk about hypothesis classes without even thinking about learning algorithm. We will make statements like, there must be an algorithm that has this guarantee. I don't know what the algorithm is, but For now though, we are talking about this particular algorithm. After eliminating all the negative examples, you take all the positive examples and find features that are 1 in all of them. So, for example, this instance eliminates this feature. This instance eliminates these two, and so on. So, whatever is left behind is a feature that's true, that's present in every positive example that we've seen, right? So, all the, in some sense, irrelevant features have been eliminated. Every positive example may eliminate some irrelevant features. You take the intersection of all of those and you produce a conjunction. But notice here in this data, the conjunction that this algorithm produces is not the same as the one that was the ground truth. The ground truth did not have an x1. And how do you, but so the question now that really, in fact, this is a discussion that we had before. The question is, the ground truth does not have x1, the learner produces a conjunction that has x1. Is this really bad? Why did it do it? Because whenever the output was 1, x1 was present in those 5 examples. So, what the learning algorithm produces is not the true concept, but only an approximation of the true function. So far so good? Any questions? And now we are asking, is this good enough? How do we know that this is okay? So, before going ahead, this is a slide that I have presented before, and I proposed an answer to this question. What was that? How do you know that this is not a bad thing? Yes?
If it classifies a large fraction of your samples correctly.
But how did we do it before? In the previous way of analyzing learning, in online learning, I'm trying to contrast what I'm going to talk about next to online learning. How did we know, how did we define good enough in online learning? Yes?
In general, we do cross-validation.
No, but that's just an experimental thing. I'm talking about a more formal. Yes?
If it stopped making mistakes.
If it stopped making mistakes. In mistake-driven online learning, that's what we did. We said, if during training this stops making mistakes, then you have learned something. That's one way of doing this. That style of analysis gave us mistake-driven algorithms, and we defined mistake-driven algorithms formally. The way we define good is the number of mistakes we make, or the number of examples that you, not number of examples, but the number of mistakes before you know that you're not going to make any more. So that's what gives you mistake-bound algorithms. Perceptron and Winnow, for example. Alternatively, we could analyze a more probabilistic intuition. That's what we'll be doing now, which is this particular feature x1 always appeared with positive examples in the training set. We never saw an example where x1 did not show up with a positive example. And the training set was maybe large. Let's say the training set was large and sufficiently big, and we never saw any positive example that did not have an x1. Maybe that's a very frequent thing. Maybe such a situation happens all the time. Maybe the probability of x1 showing up, x1 not showing up on a positive example is so rare that we are okay for the large part. Does that make sense? Now we are no longer talking about exact correctness. We are saying that bad things will happen, but not too much. And if we can quantify what bad things are and what not too much is, then we are done. That's what we are going to try to do. Is this intuition okay? Does this make sense? In fact, this is what actually gives us what's called probably approximately correct learning, the PATH framework. We have no hope of being exactly correct. We can only be approximately correct. We can't even be sure that we are going to be approximately correct all the time. Maybe the training set that we got was just this freak accident of nature that is going to ruin everything. So most likely, probably, we're going to be approximately correct. So this is called the PAC framework. This is the dominant way of, one of the dominant ways of analyzing learning. And let's talk about that and that's what we're going to talk about for the rest of this lecture and maybe the next one and maybe the one after that. The one after that is an exam. So, you might ask, okay, sure, why bother? This is just too complicated. Why do we need to do this? The mistake-bound approach was fine, it seemed reasonable, it was a theoretical approach, and it made sense. So what is wrong with it? One of the big shortcomings of the mistake-bound approach is it only says how many mistakes you will make. It never says how many examples you need to see before you make those many mistakes. Right? And this is the example that I gave in the previous, one of the earlier lectures is if I give you an automatic self-driving car that has a mistake bound of 3, it will kill only 3 people. Oh, you don't know when. Probably not a great idea. A classifier that you have a learning algorithm, you might have a mistake bound of a small number, let's say 3. But maybe you need to see 100 million examples before you hit the mistake bound. So it does not, and the problem with that is, that you might argue that's fine because most of the time you are correct, you're not making a mistake. The real problem with that is we have finite data sets. You only have these many examples, you need to know how good you can be with just this fixed data set. The mistake bound model is an adversarial model. It assumes that nature is being adversarial, it constructs the worst sequence of examples to fool your algorithm. Maybe nature is not adversarial. Probably a more reasonable assumption is to assume that there is this source of examples. We don't know what the distribution of instances will be, but there is a fixed distribution and what will be tested on will look like what we are trained on. And can we say something about that in the future, rather than making this adversarial assumption? So, really, the PAC model, it's also called batch learning. The way it works is you have a fixed training set, you train your algorithm on the fixed training set, and then you go and deploy it. And the question of interest here is not when you stop making mistakes. The question of interest here is how well will this classifier that's trained on a fixed data set do on future examples that it has never seen before. So before we slightly formalize this thing, are there any questions about this intuition? Or the connection to, or the difference from mistake bound? Just a word of warning though, we won't be looking at any concrete algorithms for a few lectures now. We'll be primarily looking at math, and eventually this math will lead to all these awesome algorithms like support vector machines, but for the next maybe 3 to 5 lectures, we're going to be just looking at theory. So let's set this up so that we are clear on the definitions. None of this should surprise you for now because you've seen this at least twice so far, but let's go through this again. We have an instance space. The instance space is the set of all possible examples, both seen and unseen. A concept space is the set of all possible target functions. It's a set of functions from which nature was allowed to make a choice. We do not get to see the target function, and you can make assumptions about. Sometimes you can make assumptions about concept space, but this could be effectively it's a set of all possible functions. The hypothesis space is a different set. Sometimes you can assume to make your life simpler. It's the same set. It's a set of all functions that the learning algorithm gets to explore. The learning is simply search over functions, right? So the hypothesis space is a search space for the learning algorithm. And it's possible that the concept space and the hypothesis space are the same. In fact, we'll often assume that it is for theoretical convenience. But in real life, we never know what the concept space is. Like, you might think of the data set that I gave you for homework 2. Who knows what the true function is? Who knows what space it lives in? In homework 2, I forced you to assume that the hypothesis space is a set of all linear classifiers. Right? And when we use machine learning, we have to effectively make this assumption. And one of the problems that often shows up is if we don't really think hard about what this hypothesis space is. We let it be a set of all functions. And then search becomes impossible. The way so there is this true function that nature would like to somehow convey to us, but nature is not in the habit of giving us functions. Instead, all we get is a set of training examples. We'll call this set S. S is a finite, that's important. It's a finite subset of X. It's a fixed set of examples on which this concept, the target function, has been applied. So you get examples like x1 that has been labeled with f of x1, x2 that's been labeled with f of x2, and you have this set of n examples. It's a fixed set. What we want is a hypothesis. What we would like is a hypothesis H that's contained in the hypothesis space such that h of x is equal to f of x. In other words, we want a hypothesis function that agrees with the target function. So, question for you guys to think about and probably answer even is, should this hypothesis agree with the target function on all examples in the training set? Or should it agree with all examples with the target function on all examples in the entire instance space? Which one's more preferable? The entire instance space, because the training set is the known quantity. I can give you a hypothesis function that agrees with the training set very trivially. It's called a database. You take the entire training set, put it in a database, and when at test time, if I have to evaluate on the training set again, I just look up the label for that example and report the label. Right? I just put all the examples in a table, and a hash table if you want, and look it up. So a hypothesis function that does perfectly on the training set is trivial to get. It's just memorizing the entire training set. What we want really is to get a hypothesis function that does well on previously unseen instances. That doesn't mean that we want it to fail on the training set also, but the true test of the quality of the function should be previously unseen instances. Is the setup, does it make sense? Are there any concerns about the setup? So there must be one question that's bothering you guys, hopefully. How on earth can we possibly make a statement about the unseen? I want my hypothesis function to be good on previously unseen function, on unseen examples. Then there seems to be a problem. If I have not seen it, how can I know that I'm going to be good on it or not? Those of you who are theory people here, or those of you who like math, will immediately jump to the answer. The answer is make an assumption. If you can't prove something, make an assumption. And assumption that we make, and this is a huge assumption that we make for batch learning, is that training instances are not going to be the ones that you're tested on. The future examples are unseen, but they are tied together in some sense, because the training examples and future examples are sampled from a fixed distribution, an unchanging distribution. It may be an unknown distribution. I don't care what it is, but the distribution is not changing. So What that means is the probability of selecting an example during training is the same as the probability of selecting that example at test time. This is a big assumption, and in the past I have found that people seem to think this assumption makes sense, but I want you to think about, is this assumption meaningful? Is this correct? And let me give you an example for this to kind of seed that thought. Let's say that your classification task is spam detection. So the instance space consists of every possible email ever, both emails that have been written and emails that have never been written. We have no idea what the concept space is. The hypothesis space could be whatever it is, let's say linear classifiers. Your training set consists of emails that, maybe some set of emails, that have been labeled as spam and not spam. And you're going to be tested on every email that has not yet been written. And what this assumption says is, you don't know what the future emails are going to look like, but future emails are going to look, I don't know what the future emails exactly are, but they're going to look exactly like, they're going to look like past emails. So if I trained a spam detector on emails from 1995, this assumption says the distribution of emails is the same. That spam detector is going to be as good in 1996 as it is in 2016. Because the distribution of emails, the nature of emails does not change. Is this a valid assumption? Too bad, that's what we have. In fact, that's the assumption that drives a lot of the theory we have in place. That said, the fact that this is, at least some of you, many of you shook your head, at least some of you vocalized this displeasure, that suggests that there's something still lacking in the theory. We probably will never touch upon that, but that's an important research question. How do you deal with changing distribution over instances? Okay, so any questions about any of this? This assumption of unchanging distribution also gives us a clean way to define what is a good running algorithm, at least a theoretically clean way. We don't care about the performance on the training set. We really care about performance on the entire instance space. But instead of measuring on the entire instance space, we are going to draw samples of instances from the instance space, and we know the distribution is fixed, and we are going to evaluate the classifier on randomly selected examples from the instance space according to the fixed distribution. So a pictorial way of thinking about it is, let's say you have, this is your instance space, and let's just, because I can only draw in 2 dimensions, let's say this is the distribution of examples. Whatever is this point here is frequently sampled. This point here is extremely rare, which means you want your classifier to be, you would rather prefer your classifier to be correct on these examples than these examples. Because these examples are rare anyway, so it's okay to make mistakes. That's the intuition. Question from the...
Will we see how models in the PAC framework allow for changes in the underlying PDF?
We won't see examples of that, and in fact that's an excellent topic for a project. We won't directly see, in a very general sense, that's an open question. We don't know how to handle that yet without making further strong assumptions, because we cannot, allowing for arbitrary changes in the PDF opens us up to things like, you're going to be trained on this distribution but tested on this distribution, so really the places that you learn or learn to ignore are the ones that are important. So arbitrary changes are dangerous, so you need to make further assumptions. We won't be looking at that, but that's an excellent topic for a project. If you're looking for suggestions on where to search, the general keyword, the names that are used in the literature are, say, domain adaptation. If the domain changes, you need your classifier to adapt. Yes?
do we also learn this distribution?
No, we don't. We are going to, we are not going to worry about that distribution at all. We are going to try to reason about learning algorithms, assuming that there is a fixed distribution, but it may be unknown.
What I'm asking is, I mean, in practice.
We won't learn. Think about the batch perceptron algorithm that you guys implemented. Did you ever make an attempt to learn the distribution? There are, by the way, learning algorithms which try to learn the distribution as well. The generative models do that, for example. We'll look at least one instance of such an algorithm. But there are algorithms that don't need to learn the distribution. That basically, instead of focusing on learning the distribution of the examples, you only learn the separator. I don't care where the examples come from, but this is the separator. So let's talk about what this fixed distribution assumption gives us. I think it gives us at least two things. The first one is this idea that by using the fact that the future is like the past, it gives us hope that anything that you learn on the training set will be meaningful on future examples. So to make this concrete in the context of this elimination algorithm, all the positive examples that you saw had x1 active in it, and the future is going to be like the past, which means that it's very likely that positive examples in the future will also have x1 in it, so you won't make too much of it. There won't be a problem. There may be positive examples which did not have x1, that feature, but it never happened in the training set. Maybe the probability of that happening is so low, and so it probably won't happen in the future, and even if it does, it will happen very infrequently. So that's the intuition, but what I just said is basically the intuition behind pack learning. This intuition is what drives the entire theory. The second thing that this fixed distribution assumption gives us is that it gives us a formal way of defining what it means, defining what error means, what the error of a hypothesis is. So let me just quickly define what that is. So let's say there is a fixed distribution D over the training set, and by examples I mean this is over the instance space X. And the function F. The error of a hypothesis on this distribution, on this fixed distribution, is simply the probability that for some X that's sampled according to this distribution, your hypothesis makes an error. In other words, for the probability that for some instance that's sampled from the instance space according to this fixed distribution, your hypothesis function disagrees with the true function on this example. Let me give you a slightly more pictorial illustration. Let's say that the instance space is X. This box contains every possible example that can ever be seen. And what is not shown here in 3 dimensions is some function that says a probability distribution on top of the space. So there might be some distribution that says maybe examples in this region are very common, examples in this region are not common. You can think of the target function as simply a function that picks out some examples and says these instances are possible. Right? It's basically just a target function can be seen as a subset of the entire space, and that subset is called the positive example set. And the hypothesis is just another function on the same space. It labels maybe another subset as positive. And notice that these two functions disagree. The hypothesis function disagrees from the target in this region and in this region. The area of that region is the error of the hypothesis. But really we don't care about the area, because what if this region here is so rare that it never happens? So really we don't care about the area, but we care about the, in a very loose sense, the weighted sum, the weighted mean of those two regions, of every point in that region. So points that are underrepresented should count less for the error. That's really the definition of probability, that an example of a random example sampled according to this fixed distribution having an error. Questions about this? This is important and it's something that you need to internalize. So think about this, and there's a question.
First of all, how can you say that it will be a one complete figure, it can be distributed?
Oh yeah, this is just a cartoon. Yeah, this is for illustration purposes only. This picture is not a scale. Yes. You could have a function that labels, yeah, you are totally right. There's no reason for it to be a convex shape.
What is the meaning of that tilde?
Okay, that's
X belong X tilde.
probability of x drawn from this distribution of what this means is this example is sampled according to that distribution, and you are looking for the probability of the error. So that's basically just bad fonts. Other questions? So when you see a definition, we'll see a lot of them going ahead. What you should ask yourself, there are two questions. One, I have given a name to some mathematical concept here. Basically, I have just defined what is called an error. The first thing you should ask yourself is, does the name mean the same as what is mathematically defined intuitively? Sometimes I could call this the accuracy of a classifier. I mean, that's completely wrong because this is measuring inequality. So you should ask yourself, is this name meaningful? And second, a slightly deeper question you should ask yourself when you see a definition is, does this thing deserve a name? You'll see, most of the times you'll see papers that have heavy math that introduce definitions here. You define a bunch of things, and then sometimes the main theorem just follows from the definition. If you are able to give a name to the right object, then the rest of the theory follows. And one of the important things that shows up in the theory of learning is the definition of an error. So stare at this and convince yourself that I'm not trying to cheat you here, not trying to fool you here and maybe one of these days I should have a slide where I'm actually trying to cheat you just to make sure that you're awake. It's early in the morning, so I know the problem. Yes.
So what you're saying is that area outside the Venn on the right would actually be smaller based on how likely that example happened.
Yes. And it should affect the quality of the classifier less, or it should affect our measurement of how good the classifier is less. Yes.
Instead of area, we think of it as like maybe a density?
Yeah, exactly that. I mean, yes, it's in fact the integral of those points according to that distribution. Yes.
So we measure this error over our training examples to estimate how often we're going to make that error in the future.
If you have to measure actually we are going to use the training examples as a surrogate for this set. But if we measure this on just our training examples, we run the risk of saying that all we care about is the training set, right?
Oh, so in other words, this would be like a running total, and if we see this, if we see this an excursion that this term takes off, then our classifier is no longer running well.
In fact, the right way to think about this is your test set. This is the reason I keep saying that you should never look at your test set, is that your test set is representing samples from this from the true distribution that you don't get to see, and the test set acts as a surrogate for this entire instance space, and it's those examples where you measure the error. the training set is meaningless. The
Yeah.
training set is only useful for picking a function. But we can't say, does that make sense though? But you don't seem convinced, so go ahead. Or you don't seem happy.
No, I guess that's just the piece I wanted, that it's a performance measure that
It's
we do on the test set,
Yes.
rather than a predictive sort of measure of errors in the future that we get from the training set.
Yes.
Okay.
That said, for now, this is mostly a theoretical construct. We will use this definition constantly to tell us whether a classifier may in the future do well in the limit. Any other questions? All right, think of them and we can come back to this. What I defined here, the error of the hypothesis, I'll also call it the true error or the generalization error. And I want to contrast that against what would be called the empirical error of the hypothesis, which is the fraction of examples in a particular set of examples that the classifier is wrong. So you can always measure the empirical error on the training set. You have a set of examples, you just count how many mistakes you made, divide by the number of examples, that's your empirical error. You cannot, in general, measure the true error because you don't know the underlying distribution. Sometimes the set of examples, the instance space may be infinite, so you cannot measure the true error because you cannot enumerate everything. So we can only measure the empirical error, and I'll use error S of H to denote the error of this hypothesis on the set S. So we have two errors. There's error D, which is the true error, and error S, which is the empirical error. And let's say we measure the empirical error on the training set, and it turns out to be very low. And suppose by some magic you're able to get the true error as well. A formal definition of overfitting is when the empirical error on the training set is much classifier than the true error. What that means is you overfit the training set. Your classifier is performing much better on the training set than what might actually be truly represented by the distribution of the training. Questions about overfitting? We've seen overfitting before, and this is just, in some sense, revisiting this thing and formalizing the definition. Yes?
How do you know that the training set isn't biased?
We are making that assumption. That's like a strong assumption that we are making. And that is the assumption that drives back learning. In some sense, what you just said, I can answer that question by saying we know that the training set is not biased because we assume the fixed distribution. It may be whatever bias the training set has will also be the bias that's in the test set. That's the assumption that drives the theory. There are actually some, even though this theory gives us beautiful math, there are places where it fails us because of that reason. We assume that's the case, but in fact we hope that's the case. Yes.
Why don't we ever want to choose bias test sets? Pick some more rare cases in our test set.
That means that you are actually, by stating that that you want to have some rare cases, what you are implying is that you have some background information that you brought from home about the nature of the true distribution, which somehow the learning algorithm did not have access to. And if you are going to do that, maybe you might also introduce that into the training process. Maybe you could oversample these, what you think are underrepresented examples, perhaps. So effectively you are changing the distribution of the examples. Alright, so let's, given this situation, and I'm going deliberately slow here, mostly so to allow all of this to sink in. Given the situation, the goal of batch learning is to devise learning algorithms that avoid overfitting. That's it. That's all we want. We want to avoid overfitting. In other words, we want learning algorithms that are not fooled by training examples that by training sets, or actually not fooled by functions that only explain the training set well. In other words, we don't want to be fooled by training sets that are actually improbable. Your training set is is simply a sample of examples. So there is some set of examples, your training set is just a collection. And the hope is we want learning algorithms that are not fooled by possibly a very freak collection, a freak accident of that generated a training set that is unrepresentative of the true distribution. How do we do that? Before talking about an example of this, I want to contrast batch learning and online learning. We've already seen online learning. We won't be revisiting online learning, so I just want to make sure that the difference is clear. In online learning, remember, we made no assumptions about the distribution of examples. We never spoke about the distribution of examples. By making no assumption about the distribution of examples, what we implicitly assume is that examples are created by an adversary. We assume that we will be tested constantly on the worst things, on the worst examples for our classifier. And that's how we get the theory. There is an implicit worst case assumption in online learning. In batch learning, we make an assumption about the distribution of examples. We still say that we don't know what the distribution of examples are. It's unknown, but it's fixed. So that's important. It's fixed and possibly unknown. We are never going to use the actual distribution itself in any of our analysis, but we will constantly use the fact that this distribution never changes. In online learning, learning is really a game between two parties. That's the learning algorithm and nature. And learning proceeds in rounds. The learning algorithm sees an example, it makes a prediction. In some sense, the game board consists of an example at a time. The move that the learner gets to make is a prediction. The move that nature gets to make is a correction. Actually, it produces a number that possibly signifies the learner's regret. We saw the mistake bound, in which the learning algorithm produces a prediction, then the oracle or nature reveals the true label, and the true label is either correct or not, at which point there's a mistake and the learner gets to update its hypothesis. That was online learning. In batch learning, there is no such fixed protocol. In fact, for the large part, we will never talk about any learning algorithm as such. Instead, we'll talk about maybe a black box learner. We will talk about the situation when examples are presented to some learning algorithm and the learner does something, I don't know what, I don't care what, and produces a hypothesis, and then you ask how well can the learning algorithm, can this fixed learning algorithm do? In order to enable that, we'll assume that the training set is sampled IID from the distribution. Who can tell me what's IID?
Independent, identically distributed.
Yes. Independent and identically distributed. Identically distributed is something that I've been talking about so far. What that means is there is a fixed distribution, every example is drawn from the same distribution. And identically distributed simply means same distribution. Independent means example number 1 and example number 2, the choice of, suppose you have two examples, 1 and 2, the choice of the second example was not influenced by which example was chosen first. So these two examples, these two random draws are made independently of each other. This IID assumption is extremely important because it makes the proofs work. So really we have one assumption, which is independent and identically distributed according to a fixed unknown distribution. That's what drives the theory behind pack learning. We don't really look into the learning algorithm, we just say this is the nature of examples that come in. What can you say about any learning algorithm? The goal of online learning, or the goal of mistake-bound learning, is to put a limit on the number of mistakes that can be made. The goal of online learning is slightly more general than that. If you are interested, you can look at what are called regret-bound algorithms. But for the purposes of this class, we looked at mistake-bound learning. We just are putting a limit on the number of mistakes the algorithm can make. The goal of batch learning is to find a hypothesis that has a low probability of making a mistake on a future exam, drawn from this fixed unknown distribution. We don't care about never making mistakes because we are willing to give up on that. Instead, we are just hoping that we will not make too many mistakes in the future. Questions about these issues?
Could you take an online learning algorithm and frame it as trying to have a low probability of mistakes by fixing the number of examples you give it?
You've already done it, by the way, in your homework. Remember that multipass perceptron, what I call the standard definition? It took an online algorithm, applied what is called an online to batch conversion technique, which is, in this case, it was just as simple as running over the data multiple times, and you got a batch algorithm. It turns out that version of the perceptron algorithm is no longer online. It is a batch algorithm because it's fixed examples, and there are these techniques that are called online to batch conversion techniques, which roughly look like that: run over the data multiple times, just shuffle the data in the middle, and you get a batch algorithm. Turns out that version of perceptron can be studied as a batch from the batch point of view. I don't know, in fact, I think, but I would be hesitant about making the following statement. I think every online learning algorithm can be converted into a batch algorithm using a similar sort of technique, but I have to check upon that. Alright, so now that we've set this up, I'm going to start defining probably approximately correct learning. Is there a question?
Yes, she has a question.
You have a question. Thank you.
So, since you have the condition IID,
Yes.
you assume that you have infinite, X is infinite, right? If it's finite, it won't, batch algorithm won't work.
Why? It could be finite, and I could
So
sample
it's finite,
with replacement.
and we sample
With replacement.
others.
Yes. You always you sample with replacement. Yes. Yeah. Otherwise, you run out. Yeah. So, for now, I'm going to. This section is important because it defines what is pack learning, and what I'm going to go through now is I'm going to go through three things. First, instead of defining pack learning in the most general setting, just to give you an intuition of the kind of results that we should expect, I'm going to analyze the simple algorithm that we saw, elimination, from the point of view of pack learning. This analysis is not general, it is tailored to this algorithm, but it has a flavor of the kind of reasoning that we'll repeatedly do again and again. And then I'll formally define what is pack learning. After that, I'll make formal connections between learning and what has been historically studied. When I say historically, probably for about 3 millennia now at least, what is now called Occam's razor. Simply that says, the principle that says, pick the easiest explanation, the smallest explanation you can. It turns out you can formally quantify Occam's razor using the pack learning, and that's what we'll do. My goal is, today I'll probably get somewhere to maybe the middle of that, and In the next lecture, I'll probably get to maybe the middle of that. And for your midterm, I'm hoping that you guys will at least know the definition of pack learning and what it implies. Okay? And the rest of it probably we won't have time, at least for the midterm. So let's start with a simple, not simple, but a situation that presents all the complexities that we have, but is tailored to this algorithm, that was conjunction. You must have, this must look awfully familiar, so I'm going to breeze through this. The elimination algorithm simply takes this data set. We are assuming that our concept space is monotone conjunctions. So capital C is monotone conjunctions, and capital H is also monotone conjunctions, and there is a fixed function that we don't have access to. Some examples show up, and the way the algorithm proceeds is you examples, you discard all of them, and then build a conjunction using the feature, build a conjunction using the features that showed up only among the positive examples. So all the ones that are in blue and italic, which I'm sure is not visible for the rest of the class. So these ones. This feature was eliminated by these two examples. Let's analyze this algorithm. Effectively, positive examples remove some features. So clearly, first of all, this algorithm is consistent with the training set. So using the terminology that I just introduced, error S of this hypothesis is 0. S is the training set. In fact, an interesting exercise for you to think about is this algorithm will always produce a conjunction that's consistent with the training set. The proof is fairly simple. You should be able to work it out. This algorithm will always produce a conjunction that is consistent with the training set. Let's analyze this thing. The first claim that I want to make is that any hypothesis that is consistent with the training set produced using the elimination algorithm will only make mistakes on positive examples in the future. It will never ever make a mistake on an example that is labeled as minus or false using the true function. Why?
Anytime it gets that example, it changes the hypothesis to...
Oh, no, this is batch learning. The hypothesis is fixed. Learning is done, and now your hypothesis is going to get evaluated on future examples. And the claim I'm making is, once learning is done, it will never make a mistake on a negative example. Yes?
It could be because it involves probabilities and for that.
There are no probabilities in this answer yet. So, yes?
It's just because it's a conjunction.
Because it's a conjunction. So, can you expand on that?
Well, so if there's an example that has a 0 in it and a relevant feature, it's going to return a label of 0. And
So let's take a concrete example. Let's say an example comes in. This example is, let's say an example comes in that's negative. You should ask yourself, why did the true function label it as negative? So can you give me an example that's negative? x1 equals
1, x2 equals 0, and then choose the rest as you'd like.
Okay, sure. So you have this. The true function will label this as negative. Why? Because x2 equals 0. The output is 1 only if x2 and x3 and x4 and x5 and x100 are all 1. So the true function will label it as negative. The learned function will obviously label it as negative because x2, 3, 4, 5 and 100 were present in every positive example. Those features never got eliminated. They would have never gotten eliminated, which means they would be present in the hypothesis, which means this learned hypothesis will never make a mistake on a negative example. Yes?
And this has to assume there's no noise.
Yeah, we are assuming there's no noise. We are assuming for the purpose of maybe this lecture and maybe even the next one, we are going to assume the case of no noise. We'll get to the noisy situation only when we come to agnostic learning. But for now, let's assume there is no noise. Well, if you have an example that looks like this, and x1 is 0. In fact, this is the only kind of an example, and x 100 is 1. The true function will label this as positive because 2, 3, 4, 5 and 100 are all 1. The hypothesis H will label this as negative because of this red box here. H requires a stronger condition. It requires x0 also to be 1 when the output is 1, for the output to be 1. Okay, so this makes sense. And if you want, I'm going to erase this mostly because I want you to create an example of your own. I've basically written the same thing. A mistake can only occur on a literal. So the word a literal is a Boolean variable or its negation. In this case, we don't have any negation, so it's just a Boolean variable. A mistake will only occur on a literal if it is present in the function that's learned, but not in the true function. In this case, like this x1. And those are the only kinds of mistakes that will happen. The opposite can never happen, and I just spoke about that. And if you want to picture that, like a crude cartoon picture of this, if these circles represent regions that are labeled as positive, the hypothesis is more restricted. It labels a strict subset of the examples that it picks as positive only a subset of the examples that the true function picks as positive. So that means that this hypothesis will never make, any hypothesis that's learned with elimination will never make a mistake on negative examples. Now, this exercise is incidentally used in the proof. The reason for this whole thing was mostly to force you to think about this hypothesis space. Before presenting the proof, let me just throw the theorem at you, and then we can worry about what it means, and then we won't have time for a proof, but I want you to get the intuition of the theorem. The theorem says, I'm going to read it out, and then we'll dissect it. Suppose we are learning a conjunctive concept, meaning the concept space and the hypothesis space are both conjunctions, with n features, n Boolean features. And let's say the dimensionality of the data is n. Sorry, the dimensionality is n. Let's say you have m training examples. The theorem says if this m is more than some number, we'll worry about what that number is later. If this m is more than some number, then with a probability that's more than 1 minus delta for some small delta, which means with high probability, the error of the learned hypothesis on the true distribution, remember that's the one that we care about, error D. The true error will be small. If you see these many examples with high probability, if you see these many examples, the algorithm will produce a conjunction that with high probability will have very small error. Now, the magic is entirely clearly in this thing in the box here, these many examples. How many examples is that? Let's look at how this depends on these parameters that we care about. The number of examples that you see is dependent on the dimensionality n as n log n. So it's n times log n. If your dimensionality gets large, you need to see more examples. Let's look at the errors of the classifier. How much error are you willing to tolerate? If you want a classifier that has a high probability, will make a very, very small error, that means you need way more examples because of this 1 over epsilon dependence. If you want a classifier that makes 0 error, this says that you need infinite examples. Which, this is a finite concept space, so that's kind of a pointless thing to say. But, a finite instance space, so that doesn't make much sense. But, if you want a target function that makes, a learned hypothesis that makes a very small error, you need a large number of examples for this kind of a guarantee. Okay, what about the delta? If you want high confidence that your classifier makes an error epsilon, then you need more examples. Why? Because you will have a log 1 over delta dependence. So, the delta is your confidence. 1 minus it's the confidence in your classifier. It's saying with high confidence, with probability greater than 1 minus delta, this learning algorithm will produce a classifier that makes small errors, error less than epsilon. These are called epsilon delta guarantees. So we'll end up proving this formally, but before the proof, any questions about the nature of this statement? Yes?
So we're not talking about what the true error actually is, we're talking about what it's likely to be.
Exactly. We can't ever say anything about what the true error actually is. What we'll say is the true error is less than epsilon. That's all we say.
Okay.
In fact, this statement can be written as probability that the true error is less than epsilon is greater than or equal to 1 minus delta. And this is where some of you might actually be shocked, because if you remember, how did I define the true error? The true error itself is a probability that h of x so the probability of the hypothesis making an error is less than epsilon is itself greater than 1 minus delta. So we're talking about probabilities on probabilities. But let's hide that for now, because that tends to make people very upset. I want you to think about this statement. There is a true error. We have no way of knowing it. All we can say is this true error, all we can hope for is the true error is less than some small number epsilon. That's an event, right? Either it's less than that epsilon or it's more than that epsilon. One of those things has to happen. Right? It's a binary. Either the true error is less than epsilon or it's more than epsilon. And the probability that the true error is less than epsilon itself is more than 1 minus delta. Now, if delta is very small and epsilon is very small, then we are in happy land. Questions? More questions? And this particular result is specifically for this algorithm, for this conjunctions. What is awesome about the pack theory is we will prove a similar sort of a result for any algorithm. In fact, we prove a result that says, I don't care what the algorithm does, I don't care what it is, if you have this concept class, we'll get a result of this kind. And that basically gives you this kind of a hammer to use on any concept class, and which you will be doing eventually. So, the next step is really to prove this assertion. We really don't have time to prove it, so I'm going to give you like an intuition for this proof, and we'll actually see the pickup on the proof formally in the next class. So, we are considering the elimination algorithm, and I'm going to be using this F and H as the running example. And the question that I asked before, what kinds of examples would make this hypothesis, would force this hypothesis to commit an error? And really, the only examples where an error will happen, as we saw before, are positive examples where x1 is absent. So, why? Because F would say false, F would say true, and H would say false on those examples. Now, why the question that really motivates this proof is, why on earth did this x1 show up in the hypothesis? It should have been eliminated, right? I mean, it was not in the true function. It should have been eliminated, but x1 did not get eliminated by any training example. Remember, a positive example in this algorithm eliminates features. So if you had an example that said x1 equals 1, or let's say x1 equals 0, x2 equals 1, blah blah blah, and the label, this particular example would have eliminated x1. But somehow x1 escaped elimination. And really the intuition of this proof is these examples that forced x1 to get eliminated did not show up during training at all. Wow, what a rare event. Not one of the training examples eliminated x1. And if you have many training examples, this rare event is even more rare, right? The probability that one training example did not eliminate x1 maybe is very small. Probability that two training examples did not eliminate x1 is smaller than that. The probability that an entire training set of m examples did not eliminate x1 is a very rare event. Now, if this rare event is extremely rare, if you put a bound of 1 minus delta on this rare event not occurring, then maybe it will not show, this rare event will not happen in the future as well. That makes sense? The proof basically is a mathematical, a formal statement of all these things that I just said. The probability that this feature did not get eliminated might have been very small, but the probability that it did not get eliminated by one example might have been very small. The probability that it survived elimination m times is exponentially smaller, and that basically would give the proof. We'll work this out more concretely in the next class. We still have a minute left, so I'm going to pause for questions. We'll pick up here in the next lecture, but are there any questions about this statement? Because this is an intuition that people often struggle with. I personally struggled with getting this for a while, but once you get it, it's pretty cool. So, any questions about this? If not, I'm going to stop now. I encourage you to revisit this lecture, just go through this argument a bit, and come back with questions, because it tends to trip people quite a bit. So, and we'll pick up on this and get to the definition of back learning in the next lecture.